Every protein in your tumor biopsy, every metabolite in your plasma, every drug candidate in your compound library, mass spectrometry identifies what it is, quantifies how much of it there is, and tells you whether it changed in a single instrument run. No other technique gives you structural identification and quantification simultaneously. That is why it runs proteomics, metabolomics, forensics, and pharmaceutical development.
Mass spectrometry measures the mass-to-charge ratio, MZ, of ionized molecules. You convert sample molecules into gas phase ions, separate them by how they travel through an electric or magnetic field, and count them by mass. The output is a spectrum, intensity on the y-axis, MZ on the x-axis. That spectrum is a molecular fingerprint, not an inferred signal, but a direct measurement of molecular mass and fragmentation pattern.
And the reason that fingerprint is definitive, the reason it goes to court, the reason it replaces every other method in clinical confirmation is structure. You are not guessing identity from a proxy signal. You are reading the molecule's mass and its fragmentation pattern directly.
The mass analyzer at the core of the instrument comes in several architectures. The Orbitrap gives you the highest mass accuracy, sub 2 parts per million, and the best resolution, which is why it dominates proteomics. The triple quadrupole sacrifices resolution for speed and sensitivity in targeted mode. It is what clinical and pharmaceutical labs use for quantitation. Time-of-flight instruments are fast and accurate, common in metabolomics and drug discovery. The choice of platform depends on whether you need identification depth, quantitation sensitivity, or throughput.
An Orbitrap Astral runs between 700,000 and 900,000 euros. A triple quad for clinical quantitation runs 150,000 to 300,000. Academic core facilities charge 300 to 500 euros per hour of instrument time. 18-month waiting lists for Orbitrap access are not unusual at major research institutions.
Subscribe to this channel. I've spent 15 years generating the mechanistic understanding you are about to receive in 12 minutes. It is free. I am choosing to be less bothered by this than I could be.
What you need: 1. An LC system upstream of the MS for proteomics, nano-LC, 200 to 400 nanoliters per minute. For metabolomics, standard HPLC. The chromatography separates your molecules by hydrophobicity before they reach the ionization source. The MS cannot select, fragment, and identify 50,000 peptide species simultaneously. The LC spreads them in time so the instrument can actually sample them.
The peak capacity of your LC system, how many species you can resolve in the gradient window, determines the depth of your proteome coverage. A 90-minute gradient on a 25-centimeter C18 column gives you a peak capacity around 500. A 200-minute gradient on a 50-centimeter column can exceed 1,000. More chromatographic resolution means more low-abundance identifications.
2. Solvents. LC-MS grade. Not HPLC grade, not analytical grade, not whatever is in the cabinet. LC-MS grade solvents have parts per billion organic impurity specifications. Standard HPLC solvents contain polymer contaminants from their storage containers, contaminants that ionize in the electrospray source in the same MZ range as your analytes.
I used the analytical grade methanol. It was the same purity on the label.
Purity on the label for analytical grade refers to organic carbon content, not to LC-MS-specific impurities. Analytical grade methanol contains plasticizer contamination. In your ESI source, those plasticizers generate chemical background noise at MZ 400 to 800. That is the main peptide detection window. Your sensitivity is already compromised before you have loaded the first sample.
Non-volatile impurities in analytical-grade solvents also accumulate on the ESI emitter tip progressively over a run. What presents as signal drift in your quality control samples is often tip fouling from solvent contamination. The contamination is invisible in the bottle. It is irreversible in the source without replacing the emitter.
It is mildly counterproductive to save 40 euros on solvent when the instrument run costs 400 euros per hour.
3. C18 reverse phase analytical column, sub 2 micron particles, 25 centimeters minimum for proteomics. Shorter columns have lower peak capacity. Co-eluting peptides compete for MS sampling time, and you miss low abundance species. 4. Sample prep reagents, reduction, alkylation, trypsin, desalting consumables. The upstream prep is where most experiments succeed or fail. Protocol. Step 1. Protein reduction and alkylation. Add dithiothrietol to 10 millimolar, 56 degrees, 45 minutes. This breaks all disulfide bonds and frees the cysteine thiols. Then, iodoacetamide to 50 millimolar, room temperature 30 minutes in the dark. This permanently caps the free thols with a carbamide or methyl group. Do not skip alkylation. Unmodified cysteines reoxidize during digestion, and your peptide coverage is permanently incomplete.
I skipped the iodoacetamide. It seemed like it only mattered for cysteine-containing peptides.
It only matters for cysteine-containing peptides, which include the active sites of a significant fraction of the enzymes, structural proteins, and disulfide-dependent receptors you are almost certainly trying to characterize. Those peptides disappear from your data without alkylation. You report the protein as present, your coverage is wrong, and you don't know what you missed.
Reoxidation after DTT removal begins within minutes. Unalkylated cysteines form new inter- and intramolecular disulfide bonds during the digestion incubation, blocking trypsin access to adjacent cleavage sites. Beyond missing peptides entirely, partial reoxidation generates an artifactual population of half-oxidized species at unexpected MZ values. The database cannot assign them, your spectrum-to-sequence match rates drop, and your false discovery rate estimate becomes unreliable.
Step 2. Trypsin digestion. Enzyme to substrate ratio 1 to 50 by mass. 37 degrees, 16 hours overnight. Trypsin cuts after every lysine and arginine, except when followed by proline. This generates peptides of 6 to 20 amino acids, the range the LC column and mass analyzer were both designed for. Stop at 16 hours. Past 20 hours without a protease inhibitor, you get non-specific cleavage events that the database will not assign.
Trypsin's strict specificity is what makes the database search computationally tractable. The search engine in silico digests every protein in the reference proteome using the same cleavage rules, builds a theoretical peptide library, and matches your measured spectra against it. If you use a nonspecific protease or allow excessive digestion time, the theoretical search space expands by orders of magnitude. Identification rates collapse because the statistical threshold for a significant match becomes unreachable.
Step 3. Desalting. Non-negotiable. C18 stage tip or desalting spin column. Equilibrate in 0.1% formic acid. Load your digest. Wash twice with 0.1% formic acid. Elute with 50% acetonitrile in 0.1% formic acid. Evaporate to dryness under nitrogen or a vacuum concentrator. Reconstitute in 2% acetonitrile, the 0.1% formic acid. This removes phosphate, SDS, urea, and every salt left over from lysis and digestion that will suppress your ionization.
I skipped the desalting. There was not enough volume after the digestion.
If you don't have enough volume, you reconstitute in a smaller final volume after desalting. You do not skip the step because your volume is low. What you just injected onto a nano-LC system is a salt solution. Your back pressure will spike within 5 minutes. Your column is being contaminated. Your first injection is already ruined.
Inorganic salts suppress electrospray ionization by competing for charge at the surface of ESI droplets. Even 25 millimolar phosphate reduces peptide ionization efficiency by 2 to 3 orders of magnitude. At physiological salt levels, the MSCs predominantly salt adducts, not peptides. No informative spectra are acquired. The experiment has failed at the injection step before a single useful spectrum is recorded.
A failed proteomics run due to skipped desalting, 90 minutes of instrument time, nano-LC column damage from salt loading, consumed digestion reagents, and potentially the sample itself, if it was a primary cell isolate or a patient biopsy. On a charged core facility Orbitrap, that morning costs between 500 and 700 euros. If the sample cannot be replaced, the experiment is over.
It is mildly notable that the most critical step in a 16-hour sample preparation protocol takes 11 minutes and is the one most frequently skipped.
Step 4, LC gradient. Sample loads in 97% water, 3% acetonitrile, 0.1% formic acid. Peptides bind to the C18 stationary phase. Acetonitrile increases over 90 minutes, from 3% to 35%. Peptides elute from least to most hydrophobic. Think of it like the coin sorter at the supermarket. Instead of sorting by coin diameter, the column is sorting tens of thousands of peptide species by the hydrophobicity of their side chains, spreading them in time so the MS can see them one group at a time.
Wait, how does a liquid coming out of a tube turn into an ion? It is still just a droplet at that point.
At the ESI source, your LC eluent flows through a fused silica emitter at 1.5 to 2.5 kilovolts. The electric field charges the liquid surface and deforms it into a cone, a Taylor cone, at the capillary tip. Charged droplets detach from the cone apex and travel toward the instrument inlet. As solvent evaporates in flight, each droplet shrinks. The surface charge density increases until the electrostatic repulsion between charges exceeds the droplet's surface tension. Ions are then ejected directly into the gas phase. Your peptides, protonated by the formic acid in the mobile phase, exit as multiply charged gas phase ions carrying 2, 3, or 4 protons each.
Think of it like a perfume atomizer, except the mist is electrically charged. Each droplet evaporates in mid-air, and what arrives at the instrument inlet is a single peptide molecule with several protons attached to it. That is what the mass analyzer sees. Step 5, MS1 survey scan. The mass analyzer takes a full scan from approximately 350 to 1600 MZ. This is your survey spectrum. It looks like a city skyline. Tall peaks are abundant ions. Short peaks are rare ones. The instrument ranks the top 10 to 20 most intense precursors from that skyline and cues them for fragmentation. This cycle, survey scan, select, fragment, runs continuously as peptides elute from the column.
In data-dependent acquisition, DDA, each precursor selection and fragmentation cycle completes in under 0.5 seconds. Modern Orbitraps acquire high-resolution MS1 data in the Orbitrap analyzer while simultaneously fragmenting precursors in the HCD cell. This parallel acquisition is what allows 20 to 30 MS2 spectra per second without sacrificing MS1 resolution or missing fast-eluting peptide peaks.
Step 6, MS2 fragmentation. The quadrupole isolates your chosen precursor within a 1.6 meters Ditz window. It enters the collision cell and collides with nitrogen gas at normalized collision energy of 27 to 32. The peptide backbone breaks at the amide bonds. B ions carry the N terminus, Y ions carry the C terminus. The mass differences between consecutive Y ions give you the amino acid sequence, one residue at a time.
A complete or near-complete Y-ion series, covering 70 to 80% of the residues, gives the database search engine enough sequence information for a high-confidence identification. The search engine matches your fragment masses against every theoretical tryptic peptide in the proteome, scores the match, and assigns the spectrum to a sequence. The score threshold is calibrated to your target false discovery rate.
I set the collision energy to 20.
HCD at 20, normalized collision energy, is below the fragmentation threshold for most tryptic peptides. Your precursor survives the collision cell intact. Your MS2 spectrum contains one peak, the unfragmented parent, and no fragment ion series. The database search returns 0 identifications. Your 90-minute run has produced nothing that can be published.
Normalized collision energy is scaled to account for precursor mass and charge state. Below the fragmentation threshold, the peptide bond cannot absorb sufficient kinetic energy to dissociate. The precursor exits the collision cell intact. The spectrum is a single peak at the precursor MZ with no sequence ions. No database assignment is possible. The run requires full reacquisition.
It is mildly ironic that setting a dimensionless number 8 units too low produces an output file that is analytically indistinguishable from an empty run.
Reacquisition due to incorrect collision energy. another 90 minutes of instrument time, another injection of a sample that may be finite. If the sample was a patient biopsy or a primary cell culture, there is no second injection. That is what instrument parameter validation is for, and that is why it is not optional.
What good data looks like. Your MS1 base peak chromatogram, a broad, irregular distribution of peaks across the gradient, not a single spike at the void, and not a late eluting blob. Your MS2 spectra, a dense Y-ion series from MZ200 upward, intense signal at low to mid-mass, minimal or absent precursor survival. Score your dataset at 1% false discovery rate on peptide spectrum matches using a target decoy search. 2 unique peptides minimum per protein for a confident identification.
The target decoy strategy generates a reversed or randomized version of your protein database and searches your spectra against both simultaneously. The proportion of reversed database hits that pass your score threshold estimates the proportion of incorrect forward database identifications. At 1% FDR, 1 in 100 identified peptides is statistically likely to be incorrect. A 2 unique peptides per protein filter applied on top of that removes single-hit identifications and reduces the protein-level error rate further. Quantitation in LC-MS runs in 2 modes. Label-free quantitation uses the MS1 precursor ion intensity, the area under the extracted ion chromatogram, as a proxy for abundance. Stable isotope labeling, TMT or SELAC, incorporates mass tags that shift peptides from different samples to distinct MZ values, enabling multiplexed comparison of 10 or more samples in a single injection. Labeling increases quantitative precision at the cost of additional sample preparation steps and reagent cost.
TMT 16-plex reagent kits run approximately €400 per experiment. At core facility rates of €300 per injection, that means 16 patient samples per single run instead of 16 separate injections. That is a €4,800 instrument cost versus €400 in reagents. The arithmetic is not subtle.
Applications. Newborn screening. Every child born in the Netherlands is screened for 30+ inherited metabolic disorders by tandem MS on a dried blood spot within 72 hours. Forensics, LC-MS-MS, is the court-admissible confirmation method because chromatographic retention time alone is not sufficient for structural identification. Mass spectrometry gives you the fragmentation pattern. That goes to court. Pharmacokinetics, plasma drug quantitation at 1 to 10 picomolar detection limits in 96 well format routinely.
Beyond LC-MS, native mass spectrometry preserves non-covalent protein complexes in the gas phase and measures stoichiometry and binding affinity directly. No crystallization required. Hydrogen deuterium exchange MS, HDX-MS, probes protein conformation and dynamics at the peptide level by monitoring deuterium incorporation rates as a function of solvent exposure. Cryo-EM tells you what a protein looks like at atomic resolution. HDX-MS tells you which parts move and how fast, and in response to binding a ligand.
I have been running unauthorized, untargeted metabolomics on every batch of kombucha I have fermented since March. 43 batches. Full LC-MS-MS, positive and negative ion mode, matched against the human metabolome database. Variables tracked. Starter culture age, T-type, sugar source, ambient temperature, brew duration, no institutional affiliation, no ethics clearance. The data folder is labeled recipes.
Batches 31 through 43 are in the -80 in your shed. I used your numbering scheme. The labels are laminated.
It is mildly escalatory that a fermented tea project now requires cryogenic sample storage and laminated archival labels.
Closing tip. Your formic acid concentration is the single variable most people get wrong without ever knowing it. 0.1% in your aqueous mobile phase, not 0.01, which gives insufficient peptide protonation and drops your ionization efficiency by a factor of 3, and not 0.5%, which degrades your retention times, broadens your peak shapes, and halves your column lifetime in injections. 0.1%. Write it on the bottle. Check it every time someone new uses the LC. That one number affects your ionization, your peak shape, and your column simultaneously. Mass spec tells you what is in your sample. But if what you are looking for is one copy of a viral genome in 10 million cells, mass spec cannot see it. There is not enough material. To detect a target that is present in trace amounts, you have to make more of it first. Next Monday, PCR. Method Monday.